So remember in January and February with projects 1 and 2 and project 3 too, when we were talking about p-values and the idea that here are two groups. The average of group A is this. The average of group B is this. It sure looks like group A is higher than group B. But is that because group A is really higher than group B? Or is that just because if I'd randomly divided people into two groups, one of them was going to be higher, and that difference that I'm looking at isn't any bigger than the amount I'd get just from randomly assigning people? That if I randomly assign them again, maybe they'd be like this, and then this, and then this, and then this. And if this difference is well within that fluctuation that comes from randomness, then we say the results are not statistically significant. And that means we cannot reject the null hypothesis. The null hypothesis is basically the hypothesis that that difference you're seeing is just the result of random fluctuation. If, on the other hand, the difference is here, even if this one's randomly fluctuating and this one's randomly fluctuating, I still can't eliminate the fact that this one's higher than this one. Even if this is as low as it might possibly be and this one is as high as it might possibly be, this one's still higher. So that difference that this one is higher than this one is not the result of randomness. If by randomly assigning them, I can never generate, randomness never generates a difference this big, then this is not a random difference. It's a real difference that comes from some fundamental difference in the data. We did that by simulation. But let's bring this back to this idea of confidence intervals. So let's say, again, I have my sample of 400 coins, but let's say I have one sample of 400 pennies, where the average penny in that sample is 24 years old with a standard deviation of 12 years. So they missed that 24-year mark by about 12 years. I have another sample of quarters. In my sample of quarters, the average age is 22 years. They're a little bit younger, with a standard deviation of 8 years. Does that mean that the average penny in circulation in the US is actually older than the average quarter? Or is it just that I happen to get an especially old sample of pennies and an especially young sample of quarters? And in fact, they're the same. Or maybe, in fact, quarters are older. I just got the youngest quarters out there and the oldest pennies out there, and that made it flip, which it looked like were true. That's the question. Is this just dumb luck? Is this just random sampling error that it happened to produce a 2-year difference? Or is that because pennies are actually older? Well, there are 3 ways to answer that question. The real way that real statisticians would answer this question is they would use statistical tests, like a student t-test or an ANOVA, or a test called Fisher's exact test, or a chi-square goodness of fit test, or any of these other statistical tests that for our purposes are essentially big, complicated formulas that require powerful computers to run, which is why statistics is such a young field. Statistics as we know it is only a couple dozen years old, as opposed to a couple hundred like calculus or a couple thousand like geometry. Statistics is very young because you need computers to do these really complicated formulas. We don't do that in this class because it's a black box. We don't know what happens inside those formulas. It spits out an answer. We don't know how to interpret it. Another way is simulations. We see if by randomly assigning coins into the category quarters and pennies, can I generate an age difference of 2 years by randomly assigning them? And I do that 100 times, and I see how often can you generate a 2-year difference. And if I can generate a 2-year difference, regardless of which one's older, 20 times out of 100, I say, you know what? Randomness does a pretty good job of explaining away a 2-year difference. 10 times out of 100, that's still okay. If 1 time out of 10, 10 times out of 100, randomness gives me a 2-year difference, then I can't really say that a 2-year difference is anything other than randomness. 5 times out of 100, that's where I start scratching my head. 5 times out of 100, I go, you know what? That's 1 time out of 20. That's not that likely. If it's less than 5 out of 100, then I say, I don't think randomness is explaining this 2-year difference very well. It's possible that it's randomness, but it's getting really unlikely. I think it's much more likely that actually pennies are older than quarters. That's why there's a 2-year difference. That's way number 2. We've done that a lot so far this year, and I've got a lot of videos on how to do that. We did that recently in Project 3 with our 100 trials, if you did that type of data. Another way to do it is to compare the 68% confidence intervals. Let's see what that looks like for this example. So again, pennies, we said I had 400 pennies with a standard deviation of 12 and a mean of 24. If you plug that into your formula, standard deviation divided by square root of number, you get a standard error of 0.6. So we would say that we think quarters are probably within 0.6 of 24. That means they're between 23.4 and 24.6. Quarters, we had 600 of them. They had a standard deviation of 8, and the average age was 22. This is all just from my setup, all from my original example. Plug that into the formula, 8 divided by square root 600, you get 0.33. So quarters, I'm pretty sure they're between 21.67 and 22.33. Notice, even if pennies were at the bottom end of their range, even if pennies were as young as they reasonably might be, and quarters were as old as they reasonably might be, pennies are still older than quarters. Even if they were at the extreme ends of their respective ranges, pennies are still older than quarters. So it's really hard to explain this difference as sampling error. This difference seems to be a real difference. How big is the real difference in the real data? Is it actually 2 years, or is it 1 year? Is it 4 years? I don't know. What I do know is it's probably not explainable away by chance. So we're going to reject the null hypothesis. This example would be statistically significant data. Moving on to do another example, let's do an example with categorical data. Let's say I have 1,000 coins I collected in the US and 20.5% were quarters. I went to other non-US nations and states and principalities that use the US dollar as their currency. Yes, there are other countries that use our currency as their official currency. Ecuador, Zimbabwe, and Timor-Leste, to name 3. And they use the US dollar as if it was their currency, but we mint it. And in those countries, in those places, I found that 25.33% of their coins were quarters. So it looks like quarters are more common outside of the US than they are inside the US. But again, is that a real difference? There's obviously a hell of a lot more than 150 quarters in circulation elsewhere in the world. I'm going to have a lot of sampling error here. Maybe the real answer is 25.33%. Maybe it's 30%. Maybe it's 10%. I don't actually know what the range is of the possible real answer for the total number of coins outside the US that are quarters. I don't know that. All I know is my sample of 150 had 25.33% quarters. So is this difference where these were more common, is this explainable away by dumb luck? Is it explainable away by the fact that both of these samples are a little bit inaccurate? Maybe this one was a little low and this one was a little high, and that's why I'm seeing a difference? Or no, really, this one's definitely higher than this one. I cannot really explain it with sampling error. Let's look at the 68% confidence intervals. So in the US, again, I'm going to plug these numbers into my formula. It's 0.205 times 1 minus 0.205 divided by 1,000, take the square root. You get 1.3%. Grab your calculator, do it if you want. Outside the US, it's 0.253 times 1 minus 0.253 divided by 150, take the square root, 3.6%. So if I look at quarters within the US, I start with my 20.5, add and subtract 1.3%, I get down to 19.2 and up to 21.8. I'll go outside the US, start with my 25.3%, add and subtract my 3.6%, I get down to 21.7 or up to 28.9. Now look at this. The highest possible age for coins inside the US is actually higher than the lowest possible age for coins outside the US. So we cannot reject the null hypothesis. Maybe all of these coins are the same age. Maybe they're all about 21.7 years old. And it just so happened we got an especially low sample from the US and especially high sample from outside the US. We don't know. Their two error ranges overlap a little bit. And if the answer is in that little bit of overlap, then maybe this is just sampling error. So we cannot reject the null hypothesis. We cannot say that this difference is statistically significant. It is not statistically significant. In other words, if we did a simulation, I predict more than 5 successes, more than 5 out of 100 times, we would be able to generate a difference of about 5 years just with random, excuse me, not 5 years, 5%. I misspoke there earlier. We'd be able to generate a difference of about 5% more coins being quarters just with random chance. That's the prediction based on what we're seeing here. One little side note. Why 68%? Why are we using the 68% confidence interval? After all, the p-value we use as our cutoff is 5%. So you might think, shouldn't you be using the 95% confidence interval? Wouldn't that fit better? Well, here's why. Let's say this right here is our quarters in the US, and this is not means, but percentages. And here's my middle value of 20.5, and then my standard error is, what did we say it was? My standard error is 1.3. And then here it is for coins outside the US. My middle value is 25.3. My standard error is 3.6. So so this is obviously further to the right. This is higher percentage of quarters than these are. In order for this to be explainable away by random chance, then the average for coins in the US has to be all the way up here. And the average for coins outside the US has to be all the way down here. This has to be high and this has to be low. Now, there's only a 16% chance, add those two numbers together, that this is all the way out here. And there's only a 16% chance that this is all the way out here. And both of those two things have to be true. This one has to be high, or this one has to be low, and also this one has to be high. Both of those two extremes have to be true for these two to be equal. And the probability that both of those 16% things are true, 0.16 times 0.16 is 2.6%. That's below our 5% threshold. So that's why we use the 68% confidence intervals, not the 95% confidence intervals. Would seem more intuitive. And there you go. Now you should have all the information you need to replace or supplement your 100 trial simulations with confidence intervals, and you can do the back of the assignment.